Okay, good morning everybody. I hope everybody's having a wonderful day. So today I'm going to be talking about this idea called Big O notation, which will connect a lot of the pieces that I've been building up to for the last few lectures. So ultimately the goal that we're going to have is the ability to compare two algorithms when I study a problem, for example, or say we're looking at a data structure which is comprised of a sequence of operations, right? I have a list of them, and I would like to know which one is the faster one or the slower one. But for more general instances, right? Because remember, we talked about a problem. Remember, a problem is an infinite collection of problem instances. And I want some way to compare. Say if I give you one problem, I want to know which of the two algorithms has a better time complexity or space complexity. And I want some way to compare them. And so we were focusing primarily on time complexity in the worst case. So I want to give you a couple of interesting observations from some of the things that we've been exploring up to this point. So last day, we talked about how we can apply the model of computation that we had, our RAM model, for counting up operations for our algorithm. So last day, I think we played around with linear search. I showed you a couple different ways to analyze linear search. And also we looked at insertion sort. So keep in mind that you can go through this exercise with any algorithm. It's just that you have to make sure you understand what the algorithm is doing. That's the first thing. If you don't understand what the algorithm is doing, then it's going to be very difficult to analyze it. And likewise, once you understand what the algorithm is, it's a matter of counting the operations as per the rules that we have. So when we did this exercise, do you remember when we derived, for example, a complexity function for linear search, we ended up with something that looked kind of like this, where I had a C1 times n plus C2. So we got something kind of like that. I think it may even be that from last day. For our complexity function, when we came up and counted up the operations by grouping constants together, or constant numbers of operations together into groupings, and we counted how many times they happened. If we do that, we get a complexity function. Now, these constants here, you might say, okay, Dan, well, what are the constants? Now, I gave you a couple of intuitions last day for what they might mean, but the point is that these constants here, they vary among the machines and it's among the machines and their given implementations. And remember, our goal is to try to compare algorithms in a way that is machine independent. So that means it shouldn't matter if I give you one computer and a different computer, as long as they are technically of the type of model that we're looking at, then it's fair to do the comparison. So what I would like to do is I would like to try to observe the fact that, hey, look, when I come up with this complexity function, for one machine, it might be the case that there's these two constants are a particular pair of values. For another machine, it might be another pair of values. But the thing is, I'm trying to represent the time complexity regardless of this fact. So that's one thing. The other thing is that I'm trying to measure the complexity of solving a problem. So when I give you an algorithm, I measure the time complexity. I get one of these functions. I want a way of capturing this for all problem instances of the given problem. So remember that for every one of the inputs, when I do worst case analysis, I look at trying to maximize the number of operations that occur, and it'll be represented by a complexity function like this. And this has to be this has to be an upper bound on that for all possible instances of the given size n. Right? Remember we talked about the complexity function is a function of the input size, right? So that's one piece of this thing. The other thing, and this is one I kind of hinted at, but I definitely did not go into much detail about at this stage, was that when we talk about comparing algorithms, you know how the other day I talked about how some algorithms for smaller inputs might actually perform better than ones for larger inputs. So keep in mind that as the input gets bigger, some algorithms may perform better than other ones. So I thought I would give you an example, but here's the thing. Remember, I ultimately want to know from a complexity standpoint, which algorithm has the better time complexity. So that means that I'm talking about all the problem instances, not just the small ones. So I wanted to illustrate this point And it's a very intuitive one. Some people will describe this as, we want to know how well the algorithm scales with respect to the input. So this is another way you can think about another phenomenon. So you're going to see that the way I'm going to motivate this is there's two pieces here. There's these constants, but also notice as the input size grows, the input size seems to matter more. So for example, if I had that hypothetical scenario where one algorithm for small inputs performs better than another algorithm, it may be the case that it's just that the other algorithm has a lot of overhead to it, a lot of setup. So that when the inputs get large enough, that setup might pay off, just as an example. So suppose I gave you algorithm A and algorithm B. And suppose I did derive a complexity function, just for the simple sake of an exercise. Suppose that these are sorting algorithms. Suppose one performs n squared many operations in the worst case, and algorithm B performs 50 times n times log n. I guess I'll make it log base 10 of n operations in the worst case. So if I were to I would tabulate this by the input size. If I look at 10, 100, 1,000, 10,000, and 100,000, and I look at how many operations happen given these two functions. If I plot it out, at first, it'll look like algorithm A is performing less operations than algorithm B, right? And this is very much like the scenario I described to you. In fact, that is true for a lot of sorting algorithms. We're going to see some algorithms where some of the ones that you've seen in 115, like insertion sort, actually perform much better for very small inputs as opposed to the much larger inputs. A phenomenon like this occurs. A trade-off seems to happen. So notice that as I make the input size larger, notice that when I get to 100, the numbers here match, right? So you're going to start noticing that there's going to be a flip of a switch here, where as the input gets bigger now, you'll notice that algorithm A is now going to start performing more operations than algorithm B does. So there seems to be some size of the input. There seems to be some trade-off that happens right about here, right? So it seems like for smaller inputs than that, it seems like algorithm A performs better than algorithm B, correct? So these are things you might consider on a practical level. No worries. So the big thing is that there is a point when I look at the input size as it gets larger. If I count up the number of operations that happen, say for one given complexity function, if I were to time that out on an actual computer, you'll find that some algorithms for smaller inputs perform better than other algorithms do. But for more general inputs, for when they get larger and larger, we see that actually this phenomenon of small inputs actually doesn't really translate. So just as the example, if I give you two algorithms, algorithm A and algorithm B, where this performs n squared operations and the other one performs 50 times n times log base 10 of n operations, both these in the worst case, if I look at that and I time it out in terms of counting the operations based on these complexity functions, if I time them out, you'll see that algorithm A performs better on smaller inputs, but there seems to be a trade-off here. It's right when it's about 100 right here. So notice right after that, algorithm B performs less operations than algorithm A does. So notice that this is another aspect or element of an algorithm when we consider it. So there seems to be this trade-off business for a given size of the input. So notice that there's these constants, and they can vary amongst the machines and implementation. And there's also this trade-off that happens at a given size of the input, where one function all of a sudden looks like, if I look at n squared, notice that these operations here, they dominate these number of operations I have in the right column. Everywhere I look after this point, the numbers on this side always are bigger than the ones in the second column here. So notice that there seems to be something interesting going on here, and I have a very natural way for us to capture both of these phenomenon. So question, if an algorithm performs more operations than other, is it better than the other? Well, we're going to see. So remember, When I say more operations than another, we have to be very careful when we say that. The point is that when we study algorithms, we're talking about all possible inputs, not just the small ones. That's the big thing here. So for smaller inputs, at a practical level, you'll have to consider the fact that some algorithms might perform better than others. So this won't be something that I'm going to capture in this discussion. Instead, I want to talk about how efficiently we can solve one problem versus another in a machine-independent way so that I don't have to worry about these constants getting in the way here. Now, one thing I will mention as a drawback that what the approach I will be presenting to you cannot capture is, for example, you notice that this function has a 50 times n times log base 10 of n. What if this constant here, this 50, was really, really big? Like say if it was like 1,000,000 or something. The approach I'm going to recommend here isn't going to be able to capture that, and that'll be one thing that somebody has to actually also consider on a practical level as well. If the complexity function, which represents the number of operations that happens, if this ends up being like a really big constant here, on a practical level, the input would have to be really, really, really big to make it pay off. For example, I don't know how big, it depends on the algorithm. So this is another thing I wanted to point out to you. So that brings me to kind of combine these two ideas so that we have a way that we can distill our discussion of comparing algorithms down in a way that I can easily compare them based on the input size. So that brings me to talking about the idea of big O notation, which is going to capture both of these things. Now, I must stress that big O notation isn't only a computer science thing. It most certainly is used all the time in other domains in the mathematical sciences sometimes. For example, types of analyses where, say, they're interested in either growth rates or, say, where the tendency gets large. Like, say if I have a given function and there's some irrelevant part that isn't really what I'm trying to study, sometimes people will use the so-called asymptotic notation to suppress those details so they can focus on what they actually are studying. This happens in some types of analytical number theory, for example. That's where a lot of this notation originally came from. But it was adapted over the years because it's very natural to the kind of things we talked about over here. So let me introduce you to the idea of asymptotics. So as the name suggests, it sounds like I'm talking about as things get big. So that's what I mean by scaling. But remember, the motivation here isn't just that. It's about studying the problem at hand, which remember is an infinite collection of problem instances, which if those inputs can be really big. So let's talk about the big O notation. And I'm going to give you the formal definition. We're going to play around with this definition today. I'll show you some concepts around the big O notation as well today. So suppose that I give you two functions, f and g. So these are two complexity functions as we defined them before. You can think of them just like when we analyzed our algorithms. I count up the number of operations. Those are complexity functions, for example. If I tell you that f is big O of g, if I write this is the exact same. That's what if and only if means over there. It says if and only if, that means that f is big O of g. If and only if whatever comes after it also is true. Likewise, if f is not big O of g, that means whatever's coming after this if and only if, this right here, if it comes after this, if that also has to be false as well. So it's an equivalency. So f is big O of g if and only if. Now, this is going to sound at first, especially if you've never seen this definition before. Most of you probably, this is the case. I'm going to parse this very carefully, and we're going to see that it actually gives us a nice game plan for how to prove a function is big O of another function. So, if and only if there exists some positive real constant c and a positive integer n0. So notice that there's these two constants that have to exist. So I'm going to underline those two things. So there exists a positive real constant c and a positive integer n0. So just keep in mind that those two constants have to exist. So this is what this statement is saying. There exists some positive real constant c and a positive integer n0 such that, so now I have to have these two constants such that the following is true. such that for all n greater or equal to n0, the following inequality is the case. It's satisfied that f of n is less than or equal to c times g of n. So that means that I have to show you that these two constants exist, and it has to be the case that when I pick these two constants, that for all n greater or equal to n0, this inequality has to be true. That f of n is less than or equal to c times g of n. Now, you might say, Dan, where does this come from? Like why should I care about this? Well, I want to show you quickly where the two pieces we just talked about might come into play and how they might be useful for us in terms of computer science. So, obviously, I don't want to use the word useful, but most certainly I want to show you the motivation behind why this definition will be very helpful for us. So, first, notice that I have a c right here. So, notice that in my first observation from last day, we had our complexity functions where we had these constants that pop up. They might, for example, measure, for example, the number of CPU cycles. They might represent different speeds that the machines might have. But the point is that I can always give you a large enough constant that I possibly can bound the most dominant terms of that given function in terms of its input size. That's the first thing. So notice that I have a constant here, kind of like what I had up over here, right? Likewise, do you remember the phenomena I talked about where we look at the input size, as it gets larger, sometimes there's these redundancies that the algorithm has, this overhead, that for a large enough value for n, notice that after that point, there's this trade-off that happens. And after that point, one algorithm will straight up, when I count up its operations, if I compare two, one will suddenly start dominating in terms of the number of operations versus another. So I want to capture that as well. You'll notice it's right here. So what that trade-off point is it's any point at the trade-off point or after that. And that trade-off point you could think of as this constant n0. So I'll show you an example of what I mean. We'll plot out a couple of complexity functions to see what I'm talking about here in a moment. But I want to first talk a little bit, well, first, are there any questions about the definition itself before I start talking about how we might use it? I'll give you some examples of how we might plot this out and get some more intuition about this. I'll tell you up front, you're going to get very cozy with this definition on the first assignment. You'll look at problem number, I guess technically you need big O for the very last part of problem 1, but it's only a matter of just stating it. You don't need it for anything else beyond that. So where does this inequality come from? So do you remember when I had that table over on the left board over there? When I tabulated them out, you can imagine that I'm looking at the complexity here and I want to organize it into an appropriate bin based on the dominant terms of that function with respect to the input size. When I do this, I want to know what are the dominant terms that appear. Now, if I'm comparing two algorithms, just to give you a hypothetical, you can imagine I have my complexity function here. I want to know that after some point, there's going to be some way that I have these two constants. These constants might represent different numbers, but the point is, it's just some constant. This inequality is going to be talking about the dominance of one function over another at some sufficient point. So keep in mind that it's just, there's going to be some point where we hit this n0 and any point after that, or n0 can obviously be any point after this trade-off point. Once we have that, we want to know which function dominates the other one, so that if we were to talk about which is faster in quotation marks, if I look at the one that f is versus the one that g is, I want to know which one dominates. G is the one that I'm curious about because that is the one that ultimately we'll try to categorize our function by. Like at large inputs, algorithms dominate. Yeah. So keep in mind that in that case, I think it's algorithm A that dominates B. So yeah, so there's this trade-off. So I'm trying to give you an intuition with this definition. So notice that there's this point n0. I'm going to show you an example of what I mean. And what I would like to do is I would like to distill the complexity of the algorithm down to an essential nugget of information. That's our big O notation. So for example, just to give you a quick example, if I were to look at this function here, I can tell you, we'll see an example like this one. I'll be able to tell you that actually this function is big O of n, for example. So notice that if I were to try proving this, you'll notice that really the terms that seem to matter to us are these terms involving the input size. The constants are just kind of redundant to us. So for a sufficiently large n, there'll be a point where these constants just don't matter anymore. And likewise, I can always find one of these constants c. But the thing is right now I just want to have a way to describe the complexity function to you without needing to go into those nitty-gritty details of these constants and things like that. But also, it also encodes or encapsulates the idea of trade-offs between two algorithms. So for example, if I give you one algorithm that runs in big O of n, and I give you another algorithm where I look at its complexity function, I prove that it's big O of n squared, I want to be able to convince you that the algorithm runs in big O of n for all inputs. For, like, if I'm looking at one algorithm versus another one, I want to be able to compare the two and say, okay, for this one problem, the time complexity is better or lower as generally when we study the problem, we would say that the first algorithm is more efficient than the second algorithm. So if this is the complexity of the first algorithm, this is the complexity of the second function, which represents the complexity for the second algorithm, then I would tell you, okay, we would go with the first one. That's what I'm trying to get at. But the point is that there are a couple drawbacks with this approach because, like I said, it doesn't capture things like small inputs. And if, say, there's the constants in our complexity function are really big, this notation will not be able to capture that. But anyways, I don't want to get into bog down into those details quite yet. I just want to talk about the definition at this stage. And we're going to be playing around with this definition a lot in this lecture. So I must note that when you read f is big O of g, I literally mean f is big O of g. So notice I'm just reading off the names of the functions. Sometimes I will say f of n is big O of g of n, just for the sake of clarity if you're writing this down on a piece of paper. So this is just to make it clear what is the input. But remember, like I said in a previous lecture, when I write an inequality like this, I literally mean the output of this function. Likewise, some people also will tell you that f is in big O of g. Another way you can also phrase this sometimes is f is of order g. So we're talking about its asymptotics when we talk about this. So I must stress that there's two common ways that big O notation is also written. You'll very often see me write f is big O of g, but you'll see that I will often also write it in the following way. Sometimes it's useful to write it in different ways, using that thing we have, the M word, the mayonnaise. Sometimes it's very helpful for us, and I'll give you some motivation behind these two usages also down here. So sometimes it's written where we have f is in, so I must stress that this is a set theoretic symbol for is in or in. So it looks kind of like an epsilon, but it's just a small little squished down e. But it's curled like that. So that's a set theoretic symbol. Sometimes there's a very meaningful way of talking about one complexity function belongs to a set of complexity functions, which I'll give you an example of what I mean by this in a moment. Second one, this is one that's very common in conventions of computer science, is using the thing that looks like an equal sign there, but I must stress it's not an equal sign. So I'll talk more about both of these in a moment here. So let's talk about these two here. I want to give you some motivation behind this definition to help you a little bit see why you might use these different symbols as well. Because I want you to just be aware of these things. Because keep in mind, I could just stop right here and just talk about this. We'll get into the nitty-gritty of that. But I want to make sure you have some familiarity of why somebody might use these different symbols. Because they are useful in different contexts. Okay, so just a couple things. So just a couple notes. So I just wanted to mention to you that formally speaking, if somebody writes f is big O of g, or you can write the n here, that's okay. I'm just writing the names of the functions. So if I write this, I must stress that this is the formal notation for doing this. It's because big O actually represents sets of complexity functions. For those that are really into making sandwiches, aka mayonnaise, mustard. I don't know, does anybody drink mustard by any odd chance? I've tried it once. Just don't do it. Just don't do it. Unless you're really into that. So I must stress that big O notation represents a set of complexity functions. Set of complexity functions. That is, if I write something like big O of g, and I say, okay, I can write this as actually a set of complexity functions, so I could give you a function f with input n such that there exists, so oftentimes people will write there exists, and symbolically as a backwards capital E, there exists a c, that's a positive real number. Remember, the Blackboard R means set of all real numbers. I put a plus by it, makes it the set of all positive real numbers. N0, which is a positive integer. Remember, that's the set of all integers. I put a plus there, the set of all positive integers. So there's our two constants like before. This is saying there exists c, which is a positive real number, and n0, that is a positive integer. For all, now this right here represents for all. It's an upside down A. For all n greater or equal to n0, such that f of n is less than or equal to c times g of n. So keep in mind in this course I won't be too overly focused on this definition, but it's very helpful to know that actually big O notation represents a set of functions. So it isn't like you could just take one set, you can add it to another set. You actually have to use set theoretic operations, but that's beyond the scope of this course. That's something you'd see probably in like, say one of the math courses you'll take this year or next year, or you've taken already before, or maybe something you might see in 310. But the thing is, I just want you to be aware that when you write big O like this, it actually can represent a set of functions. Just for example, if I gave you a set like big O, say if I give you big O of n. Big O of n, inside of big O of n, you actually have other functions. For example, you have the function n plus 5. You have other ones. You have 2 times n. N itself is in this set of functions. We have 5 times n plus 7. Like, these are all in this set. So in fact, you could take any one of these functions here, for example, and show that it is big O of n using our definition. So this is one useful way to think about big O notation, because then you can look at these as buckets of functions, and you could ask, does my bucket of functions contain your bucket of functions? So for example, one thing that we'll see is that every function that is a constant function, which would belong to something we'll call big O of 1, actually all of those functions also are in the same one as big O of n. But keep in mind that that's only because of the inequality in our definition. But we have stronger notions for these things to eliminate those, but we see those more in 340. A question. Well, for us at this stage, I think that's an appropriate way of looking at it. But one thing I must stress is that you're going to see very quickly that big O notation will represent an asymptotic upper bound on the complexity. So that means that it'll also include other functions that also are less than in terms of their dominant terms. So for example, something that you can also show as big O of n is also a function such as, I don't know, a function where it takes in 7. Sorry, like the function is literally just 7. Like it's like f of n is 7. So like you could have functions like that. Another one you might be able to show as big O of n is log base 2 of n plus 1. That's another function that's actually big O of n as well. But most certainly, you'll find that at this stage, we'll often stick to using the big O in the way that's the most closest to the function at hand. But you got to remember two things. So for us, we would like to measure the complexity and try to give the most accurate big O. So in this case, when we think about big O as the set of all linear functions, that's intuitively what I'm trying to tell you. Exactly. But also, it also includes other functions too. So it's not quite perfect. So we'll have another notion that we'll get to see in a course such as CS210. There's a notion called big theta. It's called big theta notation, which actually will contain only the linear functions. But I won't be talking about big theta here in this course. I want to keep things just to the big O. So one thing I will give us as a helpful tip is that you could think of big O notation as an asymptotic upper bound. So it means for sufficiently large input, regardless of what constant you can multiply to the function, whatever's this function here, whenever I multiply it by some constant, there's going to be a sufficiently large enough input such that any function that I compare against it, mine in here is going to dominate it. So that's actually a very good question. But yeah, for the short answer, intuitively you could just think of this as if I write big O of n, we're talking about a linear function. That's usually how we're going to use it in this course. But just be warned, there's just this caveat that it is an asymptotic upper bound. For example, I could show you that 7 is big O of n, just as an example. Most certainly, that's a wonderful question. Hopefully that answers your question. Excellent. No, good. So that I just want to show you that you can indeed categorize the functions like this. Perfect. So I want to show you the other way we might be able to use it. So you might often run into this notation. A lot of computer science people really love using this notation as well. Sometimes it's very useful. Like I said, you could literally just write f is big O of g. That's okay. That's how I define it over there. But if you want to use these, sometimes they're helpful too. You're welcome to use any of them. Just one caveat is this one is a little bit less formal in the sense as the first one. So this, I must stress, I'm going to write it explicitly because it's a very common misunderstanding where the equals sign means is. Just like I wrote over there. Means is, not equals. So you're going to see that this usage is a little bit more informal because we already just described how big O is a set of complexity functions. So I want to have some way, analytically speaking, to simplify down all my calculations so I don't have to talk about all these delicate details. I can quickly analyze it for you using algebraic notation. So this is how this usage will become very useful for us. But you're going to see very quickly that I'm going to always use it in terms of writing from the left to the right, but never treating it like an equal sign where I could go back to the left. So you're going to see this in my example here. I'll say this is often used to simplify calculations. And it's read left to right, just to be very clear. You'll see what I mean when you get to the example here. So when I have many terms, sometimes it gets a little bit bogged down in a lot of this stuff we had. For example, the other day when we analyzed insertion sort, we had like something that looked like a quadratic. We had something that looked like a linear function. Then we had something that was a constant, right? I would like to have some way I could just write this down a little bit faster if I needed to. So if I need to simplify things down, I can use this notation to do that. One key application for this idea is imagine I have an algorithm. And suppose there's 3 parts to the algorithm. Each represent, I suppose I counted these 3 parts. And I wanted to know what happens when I run the first part, the second part, then the third part. I would like to know what the time complexity is, for example. I'll show you an example how I might carry this out. So suppose that I formulated 3 complexity functions, f, and suppose f is 5n squared plus 30n plus 20. And then I'm just going to leave a little space here. So leave a little space when you're writing this down. I'm going to have g with input n. It's going to be 2n cubed minus 5. Leave a little space again there for that. And we're going to have h with input n. It's just going to be 4n. So each one of these, if I were to look at them, I'm going to give you a couple quick rules for dealing with big O notation immediately after this. But some of you might see from the exercises we've done the other day how I might treat these, right? So we know, for example, when I look at h, say h of n, so I have h is 4n, right? You would say that this is a linear function, right? So you might look at this and say, okay, well, that's big O of n, right? You're going to see that very quickly there's going to be some simple rules you could apply. I'm going to also show you some properties for how you might actually go about proving these things. So, for example, here, notice that this constant here, it doesn't really matter. For a large enough n, I could pick another constant c, and I could show you that, hey, look, 4n is big O of n. So notice the way I use the equal sign. I use it to basically drop any of the meaningless constants in front of the terms and any additional constants off to the side. So for example, if I look at g here, does anyone have any ideas what the big O for g might be? So look at it, looks like a cubic function, right? So what should go in the big O? Any ideas? So you can see right away it's a cubic function, right? Yeah, it's big O of n cubed. So question, why have you written not equals? Oh, I'm referring to, so I'm saying where equals means is, not equals. As in, this is not an equal sign. This means is, just like I wrote over there. So keep in mind that when we write it in this context, notice that when I write this right here, I'm actually saying is big O of n cubed. Same idea here. Can somebody tell me what f is in terms of big O? So you can see quite away it is a quadratic. Very good, very good. It's big O of n squared. So you'll see that we're going to often categorize our functions based on the input size, right? So notice that we've seen last day, for example, a linear function. Well, I had it here a moment ago. We had a linear function. We see the quadratic. We have a cubic over here, over there. You're going to see that these constants aren't going to really matter to us. We're going to look at the most dominant term, especially if it's given as a polynomial. Those things like quadratics, linear terms, cubics, these are all polynomials. So if I give you, for example, say something like the sum of f, g, and h, then if I give you f of n plus g of n plus h of n, since I know f is big O of n squared, I'm going to replace f of n with big O of n squared. I'm going to add this to whatever the big O is of g of n. So I have big O of n cubed. And for h, it is big O of n. So remember, in our example, f, g, and h are different complexity functions. You imagine each of these are happening one after the other. So if I sum over them, that's all the operations, right? So if I have big O of n squared, I have a big O of n cubed and a big O of n. Which one's the dominant term here? Just by the same kind of reasoning we did just a moment ago where we determined, say, g was big O of n cubed. It's the n cubed, right? This is the most dominant of these three terms, right? That are inside the big O's. So I would tell you that this all together is big O of n cubed. So do you see how when I do this, I am technically using it in a way to simplify my calculation. So I know f is big O of n squared, so I just replace that with big O of n squared, which represents the number of operations for f, which represents the complexity function for some algorithm, possibly. But remember, at this stage, I'm just talking about functions. But the whole idea is that I read it from left to right, because if I tried to reverse engineer this step, remember, based on what I just said a moment ago, there's a lot of different functions that might be big O of n, right? Including 7. So it means that it's not an equal sign. You know that, say, 5n squared plus 30n plus 20 is not the same as 7. In fact, they have completely different asymptotic orders. One's a constant function, one's in fact a quadratic, right? So this is one way you can also use the big O notation. You'll find very often that this is a very handy way of abbreviating your work. So I must stress that technically using it this way, some see it as an abuse of notation because you're overriding the use of the equal sign to use it algebraically. And likewise, now keep in mind, there's nothing inherently wrong with doing that if you define things carefully. Just like if you're doing things when we describe an algorithm, but there's other issues like if I want to treat big O like a set, I would have to define what plus means for that, and in our conventional algebraic way, it doesn't work like that. I would have to define a new version or an override of that operation. So that's something, for example, you might be familiar with the idea of overriding operations. That's something I know that you'll see on the labs, except you think of it from the mathematical level, the mayonnaise, is that you make your own addition operation that would behave that way. But yeah. So are there any questions about these two? I just wanted to expose you to these two just so that you have some familiarity with like, oh yeah, it could be a set, but I can also use it in a way to simplify my calculations. But very often you'll find I'll just focus primarily on this and you having an intuition for the second usage. So keep in mind, I'm not expecting you to be a master at this. We're going to spend a lot of time just using the intuition behind the second usage. But you'll see me sometimes use this symbol too, sometimes. So I'm going to first give you a couple of rules, then we'll talk about different kinds of functions that we might categorize things or buckets. So remember I talked about these buckets? I would like to have some way of giving you a nice set of these buckets, so you know which one is which bucket and why we call them those. And then I'll give some examples of us trying to prove some of these big O claims. So if we're okay with that, give me 2 thumbs up. I just want to get a flavor for where everybody's at. Excellent, excellent. So keep in mind, we will be doing plenty of examples. There will also be plenty of examples in the notes. So keep in mind that I'm not expecting to be like a master at this stage, but as long as you're following me for most of this, we're all good. So I'm going to first give you a couple quick rules for, you know how we determine these big O's here? And we said, oh, well, that's a quadratic, right? And we had some very basic ideas I just mentioned. I'm going to give you a couple quick rules for simplifying down to determine what the big O might be. And then we're going to start really getting ourselves knee-deep in the idea of proving big O claims. So let's do this. Yeah, well, these are a lot of concepts. We're talking about a lot of different things at once. That's understandable. So I'm going to first give you a couple simple rules. So remember, you always got to be careful with what you're looking at first. So these are a couple simple rules. So very often you may have to just look at what the function is at hand. and see if these maybe might be applicable. But you'll find at the stage that we're going to be working at, almost always we're going to be counting the operations. So for example, on the first assignment, you'll be counting operations, right, to determine a complexity function. But if you're eyeballing a function like this, just like what we talked about, oh, there's a linear function, that's a quadratic. You'll find very quickly that a lot of these rules are going to fall into those compartments, that activity we did. So the first one is that you can drop, so quote unquote, you can ignore multiplicative and additive constants. I'll give you an example. So just as a quick example, if I give you 5n plus 3, what I'm saying is that you can straight up ignore the 5, you can ignore the 3, and you can just say, oh, this is big O of n. So multiplicative and additive constants, they don't matter. They don't matter in the big O. Another one is that if you're, say, given a bunch of terms, the one you have to focus on is the most dominant term. So this very often occurs when you're given a polynomial. So polynomials are very easy to identify the most dominant term. So we're going to get some familiarity with this throughout this course, and I'll talk about different classes of functions based on the least dominant to the most dominant in a moment here. So consider the most dominant term. Most dominant term in the expression. For example, if it's a polynomial, take the highest degree polynomial term. I'll just rephrase that as take the highest degree polynomial. So I'll give you an example of what I mean. It's actually very similar to the examples actually we've been seeing. So suppose I give you 8n cubed plus n squared plus n plus 1,000. So by the first rule, you see that, okay, well, this 1,000 doesn't matter. The fact there's an 8 in front of the n cubed doesn't really matter. So can somebody tell me what the big O is for this? It's n cubed. This is a cubic function. So the reason why I did is because, look, this is the most dominant term. Look, it has the largest exponent. Now, one thing I have to warn you about, this is one caveat to this rule, is that sometimes you have a sequence of things that you're adding. Now, each individual term might not look very big, but when you add them together, they actually represent something that actually might take the form of a polynomial or even an exponential function. There's actually an example akin to this actually on the assignment, where you actually will have it where you're proving using the definition of big O a whole bunch of constant terms. For example, just to give you an idea what I mean, for example, we have 1 plus 2 plus 3 plus 4 all the way up to n. One common mistake you might make if you literally took this, and it's like the most literal sense, you might look at this and say, oh, that's a constant, this is a constant, that's a constant, but that's an n right there. That's a big mistake because the way this is formulated is actually in terms of n. So you can't actually use that rule here because the definition of this sum is actually in terms of the sequence here. It's actually, there's n terms. There isn't a constant number of terms. This is not the same as here where I have exactly 4 terms. So in this case, you'd make a mistake if you said it was big O of n. This is big O of n squared. The way you know that is because this actually yields the closed form expression. We have n times n plus 1 over 2 from last day. And that ends up being a quadratic. So Are there any questions about these two basic rules? So these are just kind of some simple rules you can try using. If you ever are trying to eyeball a given function, you're like, okay, well, what's the big O? These are a couple that'll be very helpful for doing that. So if there aren't any questions, I want to start talking about different kinds of complexity functions. So these are often bucketed by big O, using big O notation. So that we can talk about, does the algorithm run in quadratic time? Does it run in linear time? I would like to be able to categorize it so that I can compare two algorithmic running times based on their big O's. So the big O notation that represents their complexity function. So I want to be able to take two algorithms, and suppose I tell you the worst case time complexity is big O of one function, and I have another algorithm for that same problem, and I want to say, hey, look, its complexity function is big O of this. I want to be able to compare the two and say, which one in the worst case seems to be more appropriate? And that's where we're going with this. So let's talk a little bit about that. So I'm going to list out some functions that are going to be very relevant for us. I'm not claiming that this is a complete list. These are just some common classes of functions. So let's talk about this. So I want to give you, I just want to reinforce, big O is an asymptotic upper bound. So that's the thing you got to keep in mind. So that means that all sorts of functions are actually contained in one big O notation of a given function. But those functions actually all those ones in one bucket may actually belong also in another larger bucket that actually contains it. So for example, I can have one bucket that's actually inside of another bucket. So I'm going to list out these buckets from small list, because these are technically an infinite set of functions, each one. I'm just saying that one contains the other. I'm going to start at the most specific to broader. You can think of this as least dominant to most dominant, or lowest to highest. So I want you to be aware of the following classes. The following classes of complexity functions. So I'm ordering these by containment. So some people would write this, for example, so this is by containment. So if you think of these as sets, like I said for my first usage. Some people in set theory would write this as a proper subset. So it's a symbol that looks like this. So I'm going to start off where we might think we might have to start is actually at the constant functions. So we have big O of 1. These are the constant functions. So if somebody says big O of 1, they're talking about constant time. For example, if we're talking about time complexity. So for example, if I just have an algorithm that just assigns the value assigns to a variable x the value 5 and just ceases from there, it performs just some constant number of operations, right? Well, that's just a constant, right? I would tell you that that algorithm runs in big O of 1 time. And you might ask, why a 1? Like, why isn't it like big O of c where there's a constant right there? Well, I don't know what the c is. But the point is that, as you're going to see in your exercises on the assignment, that when I give you something that's like big O of 1, or I give you some number that's inside of here that's a constant, you can usually find a bigger constant by selecting that as one of the two constants. So another one that I want you to be aware of is big O of log n. These are the set of logarithmic functions. So these are our logarithmic functions. I must stress that typically in computer science circles, when I write log n like this, just presume I'm saying log base 2 of n, but I must stress that the base of the logarithm actually doesn't matter in big O. So for example, if I wrote log base 10 of n plus 1, and I said, I asked if that's big O of log base 2 of n. The answer, of course, is yes. In fact, there's an exercise it's kind of like this one, actually, on the assignment. You'll get to see how you could go from one base of a logarithm to another, and it ends up, and as a result, just to give you a little bit of a heads up, it may end up being just a constant term, that conversion. So big O of n, we've seen this one before. It's linear. So we'd say, if I give you an algorithm that runs in big O of n worst case time, I'll tell you it runs in linear time with respect to the input size in this case. Note that sometimes when we talk about the complexity of an algorithm, we may have multiple parameters that appear as the input size. Keep in mind how they're written. That also will help you dictate what kind of function it is. But I'm not going to talk about that here. It's more something that we'll talk more about in something like CS340. So another one is big O of n log n. So some people, usually people will just say it's big O of n log n, we'll just leave it at that. Some people call this log linear, but it's not a very common term, just to be clear. It's used in much more technical circles. So usually if you're talking to somebody, just say big O of n log n. They'll know what you mean. Big O of n squared, we already said that's quadratic. So one thing I want to emphasize is if I give you any one function that's in big O of 1, or is big O of 1, it also is big O of n. It also is big O of n squared. Like I said, it's an asymptotic upper bound. So there's the distinction that we're going to have in this class is we're going to try to aim for the closest asymptotic bucket. So one of these sets of functions, I'm going to try to categorize it to the one that's closest to the one I'm interested in. But I must stress that there's a difference between how we analyze the algorithm and the mathematics of big O notation. So I must stress that there's two different things in play here. So another thing, we also can have the idea of a polynomial. So much more generally. So for here, this is just some constant c greater or equal to 0. So this is for any one constant c greater or equal to 0. So for example, things like big O of n cubed, that's a polynomial. Big O, notice it's a big O here, by the way. It's an asymptotic upper bound. So remember, that will contain all of these ones that are just above it. So if somebody tells you that an algorithm runs in polynomial time, it could technically be that the running time is logarithmic. It could be that it also runs, it could be that it runs in n log n time in the much more carefully analyzed way. But the point is you look at it as an upper bound on the running time. But usually we'll aim for the most accurate one, not the loosest one. So I want to mention, one thing I must mention is that normally when we study tougher problems, all the ones I listed here typically are considered efficient. But for very, very easy or very narrowly studied problems, the difference between quadratic and linear might be a big deal. The difference between quadratic and logarithmic, or even linear with logarithmic, will be a big deal. Because you got to keep in mind logarithmic time, that's the inverse of exponential time. So that means that it's growing in a way that's inverse to an exponential function. That's a lot slower than, say, a linear function. So having a running time that's logarithmic versus linear actually can make a very big difference in practice. So I want to mention some other ones. For example, there's big O of c to the n. This is what we'd call an exponential. So this is the set of all exponential functions. So this is for a constant c greater than 1. Now there's even more that are beyond this. For example, there's factorial. Once you start getting into running times that are up here, you might be starting, especially if you're not considering a problem that's considered tough. I'll keep very loose with that language of what a tough problem would be. That's not something I'll focus so much on in this course. But if you start getting running times that are exponential or factorial, somebody might give you a weird look if they see that this problem is actually a pretty easy one to solve. These are much slower. These are much slower running times. So for example, exponential would be like 2 to the power of n. If you want to get even wilder, you can have running times like big O of n to the power of n. I don't even know what that's called, by the way. It just, I would not recommend you do that one if it's possible. There's a very small set. It's still technically infinite of problems that I could even fathom that would require running times that would even require that if we're talking about solvable problems. There's a very small number of problems that would fall into that category. Most of the problems that we're going to study in this course, the running times that we'll run into will fall more into this camp, or say anywhere from polynomial and up. That's what we'll focus on mostly in this course when we come to running times for solving problems, because those are deemed efficient when we start studying these kinds of problems. So are there any questions about these kinds of functions at all, or is this seem pretty straightforward? I'm just giving you some of the common categorizations for functions. So when I start talking about running times, I'll tell you, that the running time is big O of n log n in the worst case. You'll understand what I mean, right? Excellent, excellent. So it just means that there's the complexity function. When I derive that I know that it belongs to this set of functions. So anyways, I thought I would talk a bit more about how we use the definition of big O. So I thought I would plot out a couple functions so that you could get an idea for these two constants. Then we'll actually start playing around with the definition, because that's going to be considered rather important for especially the assignment if you start playing around with this. So I'm going to plot out two functions just to give us a flavor for this definition. So remember, the definition has these two constants, c and n0. So suppose I have 2, 4, 6, 8, 10, 12, 14. Let's go up to 16. And we'll have 0, 0. We'll have 1, 2, 3, 4. I'll label my axes. So n is going to be the horizontal axis. The vertical axis is going to label what the output of the two functions I'm going to look at are. So I want to suppose that I give you two functions here. So suppose that f is going to be 2n, and I have g, which is going to be n squared. So suppose I give you these two functions. So I'm going to start off by attempting to plot freestyle what 2n is on the board here. So I'm going to start off by plotting out, usually it's a good idea to kind of make some dots to help me do this. 2, 4, 6, 8. So it'll be a line that looks something like this. I apologize for my line. It's not quite straight. I should bring a meter stick sometime. So this, for example, that's 2n right there, right? And if I look at n squared, it'll be a shape of a parabola. So it'll be something like this, like 1. Because remember, 1 squared is just 1. 2 squared is 4. 3 squared is 9. So you're going to end up with something that looks something like this. Oh man, that quadratic is getting botched really good, man. That quadratic fell into, I don't know what. It got put in the microwave a little too long. Like a really bad Tupperware container. But that is our quadratic here. This is g. But here's the point. Here's the point. So when I determine f is big O of g, for example, if I wanted to do that in this example, or I wanted to just compare these two functions. So what I would do is there's kind of seems to be two things that are of interest to us. Now, first, because I plotted them out literally using the two functions, I'm going to assume that c is just 1 here. Because remember, at the end of the day, there's going to be this inequality. It says f of n is less than or equal to c times g of n. If I make c equal to 1, then I'm comparing f and g against each other. So it means that if I were to make c equal to 2, I would take this quadratic and I would multiply each one of its outputs by 2, right? So this would get stretched by a factor of 2. So now, here's the thing. If I pick C to be 1, notice that one way I could figure out where this trade-off occurs that we've been talking about is where they intersect each other. So notice that I have an intersection right here at 2. But notice that G begins to dominate F at all points after this. So whenever I consider, like, say, 3, notice that if I look at F and I look at G, G's above F after that point. So notice that this trade-off point, this value for n0, if I make n0 be 2, notice that if I pick these two constants, then I could show you, or at least the idea is that there's some argument I can make to show that f of n is less or equal to c times g of n for all n greater or equal to 2. So one thing I need to note is that n0 could be this point right at 2, or it could be anywhere after this. Because remember, everywhere after this, g is always going to be above f in the plot here. So I want to first mention that one way you can derive, so if you pick a c and then you figure out what n0 is, one way you can do this is by using root solving. So you take, say, for example, the difference of these two functions, or one way or the other way, and then you would try to find those, you try to solve for the roots and you find the largest one. One drawback of this approach is that it relies on knowing things about the functions and their behavior. So rather than appealing to calculus, I want to show you some very simple and elementary ways to argue that in this case, for example, f is big O of g, just as an example. But to do this, I want to give you some tricks to do this. So I wouldn't call them tricks, they're just some standard ways to achieve this. But indeed, I could use these two constants, and notice that for my definition of big O, I could show you that 2n is less than or equal to 1 times n squared for all n greater or equal to 2. So if I could show that that inequality is always satisfied for all n greater or equal to 2, I'm done. So the game plan for us when we try to prove these big O claims is I find c and n0 such that this inequality always is satisfied whenever n is greater or equal to n0. So that's going to be the strategy we're going to use to prove big O claims. But you're going to see I'm not going to so much focus on plotting them out like this. These are folly with faults based on only knowing things about their functions and their behavior. We might have different kinds of complexity functions, and it might become very difficult to just simply plot them and point them out. Now, you can do that, but I'm going to show you some techniques to easily prove to somebody that indeed f would be big O of g. So just remember, the big game plan is to find those two constants, c and n0, such that this inequality is going to work for all n greater or equal to n0. The for all n greater or equal to n0 part is very important in this. A very common mistake students make is they forget about that. They just plug in n0 and they just assume it works. That's not how it works, unfortunately. You need a little bit more than that. So I thought we would do some examples. So I must stress that I do have a little bit more details on how you might do some of this algebra to, say, solve for the roots in the notes, but I'm not going to focus on that so much here because that's not really the point of the exercises I'm going to do with you here. Instead, I want to focus in on how you can prove that f is big O of g using as few assumptions as we can. Why? Because it's easier to convince somebody when you don't have to assume as many things. So you're going to see a lot of tricks that you know about certain kinds of functions are going to be very helpful here. But at the same time, like I said, there's a lot of different ways you can find these two constants. You can do root solving, but I'm not going to focus so much on that because that relies on me knowing that certain functions are increasing or decreasing and things like that. I'd rather focus on just simply adding things into buckets, which I think is a little bit more elementary than just doing that. But I'll first just dive head in. We'll start doing some examples and we'll see if we can sharpen up our craft here. So we'll start off with an example. So I want to first start off by showing, I want to show that n plus 5 is big O of n. So I'm going to start off by just trying to do this example with you. So the first thing, we have to appeal to the definition of big O. So remember, the definition of big O says there exists constant C and constant n0. C is a positive real number, n0 is a positive integer. Remember that they do belong to these two kinds of numbers. So that's very important in this definition. You have to find the two constants, and our goal is to convince you once I pick these two that they in fact do work, such that the inequality is going to get satisfied for all n greater or equal to n0. That's going to be what we're going to try to do. So I'm going to first tell you what we're going to try to do. That's usually a good way to start off a proof, is tell the reader what is going on. So I'm just going to say we need to find constants C, which is a positive real number, and n0, which is a positive integer, such that for all n greater or equal to n0, n plus 5 is less than or equal to c times n. So notice all I've done is I've substituted in the functions that are just into the definition, but I'm phrasing it in terms of what I'm trying to prove to you. So I'm just going to try finding these two constants so that when I get the two constants, I can present them to you and say, hey, use the definition of big O, there's the constants, and this is why they work. That's the goal with our proof here. That's at least the strategy I'm going to show you. It's a very common and easy way to do this. You're going to find I'm going to give you a lot of ways to easily formulate this. So we'll do one example. We'll see how much time we have to do another example. And then we'll start really getting into this with one or two more after this on next class. But we'll see what we got here. So I'm going to first start off. Now, I'm going to first show you how you could go about it. But we're going to see more techniques that actually make it even easier to prove the claim than just this. I just want to show you that you could just find one of the constants and determine the other one in a way that isn't just simply, I look and plot them out and I figure out where the trade-off point is. That isn't a formal proof, by the way. It's just a picture. So we need actual formal proof to do this. So keep in mind, we're trying to prove the claim. Now, I could just convince somebody with a picture, but that's not really the goal here, is I want to prove it to you. And how do I do that? I can use the definition. So I'm going to start off by just I'm going to try picking C is equal to 2. You might ask, Dad, why'd you pick 2? I'm telling you, some constants work, some won't. This one I just picked out of a hat, just to make the algebra a little easier. So sometimes I recommend just working off the side on some scrap paper, just fiddle around with some of the algebra. But I will be showing you ways to much easier approach these. So next class, I'll be showing you more of that. So I'm going to pick C is equal to 2. Then I'm just going to say what I'm going to do next. Then we need to find n0 such that n plus 5 is less than or equal to 2 times n for all n greater or equal to n0. So notice here that I have a linear term here and a linear term over there. What I'm going to do naturally is I'm going to try to subtract the n. I'm going to try to take away an n on one of these two sides so that I get something that looks like it'll easily tell me what n0 can be. So a very natural way to do that is to subtract n from both sides. Then 2n is greater or equal to n plus 5 if and only if n is greater or equal to 5. So notice that if you subtract n off of both sides, so notice that if I subtract n for both sides of this inequality over here, you end up with n is greater or equal to 5 because there's an n on the right-hand side over there. So notice that I get n is greater or equal to 5. So does anyone have any ideas what I should pick for n0 here? So what should n0, what can I pick as n0? So remember, the whole idea is that n0 is going to be anywhere on or after the trade-off point. So where I get it, where it indeed will be the case that this inequality is going to be true for all n greater or equal to that value. So I just did some algebraic tricks to show you that I could simplify that down, and it will actually literally tell me n is greater or equal to 5. So I'm just going to pick 5, right? I must stress that technically speaking, n0 could be 6, 7, it could be 10,000, but I'll make it 5 because that seems to be a nice number because it falls from our reasoning. So I'll pick 5, and then I'll say, therefore, by the definition of big O, so because I have my two constants, I showed you why it works, and I'm now going to present the definition of big O to you. Therefore, by the definition of big O, n plus 5 is big O of n. And that's the end of the proof. So I put a box there to indicate the end of the proof. So this is how you could prove the big O claim. So notice that I find the two constants, but one common strategy you'll find is that you pick one of the constants and then you derive the other one. Because if you just pick out of a hat one constant and then you justify the other constant, as long as the reasoning for selecting the other constant works, both of them should work. But I'm going to give you, next class, I'm going to give you more intuition for how you could pick C much better than this. So that being said, because we're out of time here today, when we come back, we'll do some more examples of proving that a function is big O of another function, and I'll show you how you could show that f is not big O of a function. So that being said, when we come back, we'll have a lot of fun doing this, and I want to wish you the best for your day, and have yourself a beautiful day. I'll see you tomorrow.